Leetcode 206, reverse linked list. It's an easy problem and definitely not one of the easiest, but still it's an entry-level problem when it comes to linked lists. Yeah, so nothing fancy happens here, just the one of the most standard operations, a reversion for a linked list. Yeah, so if you are new to this topic and linked list seems confusing to you, then definitely give it a try. And here is the description, very short. Given the head of a singly linked list, reverse the list and return the reversed list. Yeah, and one of the most confusing things when it comes to lists, trees, graphs, and so on, is that usually they are given in some modified form where we don't have like a single object which is represents the whole list or the whole tree and so on, but we have either an array representation or we have just an object which represents a single element. And in this case, the single element is the head. And as you can see on the right side, let's take a look. We have this class called list node, which represents nodes of the list. Yeah, and those are the individual building blocks of the list. But there's no such object or such data structure as the whole list. And so basically, you will have the object of this class, which stores two things: the value, the label or the data which it stores, and a pointer to the next element, which is again an object of this class, or none, yeah, in case it is the last element called tail. Yeah, so we will have an object of this class given as input. That will be the head, and that's all we have. And then we'll have to traverse using those next pointers and get to the end, again to the last element. And of course, as we go, we will have to reverse, meaning that the arrows will have to point in the other direction as they're pointing in the beginning. Yeah, and here in the first example, you can see that we have 1, 2, 3, 4, 5. Yeah, but it doesn't have to be this way. Basically, the numbers or the data that it stores is meaningless for us and doesn't have to be sorted or come in any sort of order. The only thing that we care about are those connections. Yeah, so the data itself, those values, we will never access it in our code. It's just something which is given additionally. And for us, it's simply a noise. Yeah, so we will not ever use it. We will just be dealing with those pointers to the next element, and we will try to reverse, meaning that the arrow will point in the other direction, and we will try two approaches, which I think there are like two basic ones. There are probably some other more advanced, but the first one is iterative, where we go one by one, and as we go, we already will be switching the arrows or reversing the arrows, those in the other direction. Or the other approach will be recursive one, where first we will recurse to the last element, and then we will be going or backtracking one by one and reversing as we backtrack. So those are the two approaches. And ironically, the first one is, I think, simpler, easier to understand, and faster. Yeah, but still, it's good to have a good mental model of recursion, since it's very useful for everything linked lists, trees, graphs related. And it's good to train it on such an easy problem. And so we'll do it for comparison. And that's more or less it. So as you can see, they just reversed the arrows. Yeah, and here they reversed the order. So the last element is now drawn as the first element, but basically they could also swap the direction of arrows. It's just a graphical representation. Doesn't matter. And those inputs, of course, here are given as arrays and outputs, but that's not what we will be dealing with. We are dealing with objects of the following class, the list node. And the second example is just an easier version of the first example. Here you have 1, 2, and then 2, 1. And the last example is an edge case where, of course, it's an optional. So it could be the case that there is none, which we have to handle as well. Yeah. So it could be the case that there are no object is provided for us. It's simply none. and follow up. A linked list can be reversed either iteratively or recursively. Could you implement both? Yeah, that's what we want to do. So let's think about what I was just trying to explain. So 1, make it XL, like this, and here 1, 2, maybe the arrows can be this. And the last element 5. I can make it smaller like this. Okay. And let me also update the values so they look different. We can recognize which is which. And our task is to reverse the linked list. And first approach that we use will be iterative. We will create 2 additional variables. Previous and current, which will store the previous node and the current node. And first we'll initialize current to the head, to the one that we get as the first input, and previous to none. So the first previous is outside of the list. And then as we go, we'll be progressing previous and current, and we will be updating the current next. Update current next to point to the previous. But before we do this, if we just use those 2 elements, this wouldn't be enough. Let's say, let's draw them. So let's say this is our previous. First it points outside, and this is our current. First it points to the head, and we try to update. So if we do this and we make, let's change it. So this is our current, and if we try to update the connection and point to the previous, which at this point is none, then we will lose the rest of the list. So we need an additional variable. So maybe 3 additional variables: previous, current, and next. And first, we will store or maybe update next first to point to not to point to store the next element in the list. Then update current next, and then progress both current and pref. And actually, first we update the pref, the previous, and then the current, and that's it. And that's the whole philosophy. So let's do it. So first we initialize previous. It is our green one. Let me just add the colors here so you're not confused. Maybe even like this. Previous, current, and next. And next initially doesn't exist. Then we access the first current. So where is the current pointing to? And we get through its pointer, through this point next, we get this element. And here is pointing next. And now we can do our trick. We can update next first to store the next element in the list. So we remove this. Sorry, this we already did. Now we do the third point. Yeah. So this second point is just creating the orange arrow. Yeah. Then we update current next to point to the previous, and in this case it points to none because the green one points to that. And then we progress both previous and current, meaning that first we update previous. This is the previous points to whatever current is pointing to, is storing right now. And then current goes to where the next was. Where the next is. And that's it. And we repeat this process through each element. Yeah, so now we leave it alone. And the next is this one. The current is this one. Then we do the update, point to where the previous is pointing, and we update previous and current. And we do it multiple times. We first do this, then we do this, then we do this, and the last we progress both, and so on and so forth. And of course, if the list was bigger, then we would do it a couple more times, but I think that you get it at this point, and that's it. So that's the whole story with the iterative approach. Let's first implement it, then we'll go back to discuss the recursive. So we need previous and current, which we already said that will be none and head. And while there are still something in current, we haven't reached the end, we will do those steps. So first we update next. Next is pointing to current next. Then we update current next to point to the previous. We swap. And current next is pointing to the previous. And now we progress both previous and current. But first, previous is pointing to where current was before, and current goes to where next was before. That's it. And we have to return the new head, which will be in previous, because we'll be moving them till we reach the end, and by the very end, next and current will be outside of the list, and previous will be pointing to the last element of the original list, which is the new head. You can try run. And runtime error. Built-in function or method object has no attribute next. Why is that so? For which? Current should be pointing to the head. Okay, I see. The typo is here. I use NXT here, and here I use next. Okay, let's try again. And the first two cases accepted, so probably we are good to go, and we beat 100% of other users. Okay, so now let's discuss the recursive approach, and we will use the same list. So maybe let me. Can I undo the changes? No. Let me just copy this and let me recreate the list. Like this. And I will copy the arrow. Okay, now we have the original list back and we can discuss the recursive approach. So, first, we'll recurse till the end of the list. So in recursive functions, usually you have two cases, base case and the recursive case. And in our case, the base case will represent the case where we go to the end when we have reached the very last element. And we can check it by checking if either the element is none or it's pointing to none. That means that we have reached the end. And then we will backtrack. And as we backtrack, we will do something. And then as we backtrack, update the pointers by, and now what do we want to do? By reversing what is the next, pointing to the current, and by reversing where is the next pointing to, and removing the previous connection. Yeah, so basically we would reach the end. We would go like this. Recurse, 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 recurse. Then backtrack. And at this point, we haven't yet changed any arrows, any connections. And now we have to reverse this one. And how can we get this one? We know where this is pointing to, so we get the next, yeah? And we reverse it. We have this and we have this. Yeah, we reverse where it's pointing to by first updating like this. And then we also have to remove the old one. Yeah, because this will still be there. So we have to do like two operations at this point, and then we'll be backtracking one by one and doing this all the time. Yeah, so we'll reverse, 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 and each time remove, remove, remove. Yeah, that's more or less the idea. The only thing which we'll have to keep are all the additional nodes, so we will use more space than here. Yeah, here we use basically O1 space. Both of them are ON when it comes to time, but this one uses more space. So here, for example, we beat 80% when it comes to space. And as we implement this approach, probably our memory usage will increase. So let's comment it out and try to do the recursive version. First, the base case is if head is none or head next is none. Put this up. That's how we know that we have reached the end. Okay, so now we have this case. And now we have reached the end and we can return simply the head. Yeah. And the other normal case or the recursive case is where all the magic happens. Recursive case And here, first we call the function itself. Yes, that's what recursion is all about. And we, of course, want to move forward. So the only way to move forward is to call the next, to get the next element. And now we do this trick with those arrows, as I stated here. And this might be a bit confusing. So how do you get the next element? The next element is next. And how do you get where the next element is pointing to? Have to do head, next, next. Yeah. And where do you want it to point? To head. So you can think about it for some time. If you don't get it at first, this is this arrow. Yeah. So head next is this. Then head next is where this is pointing to, and you want to reverse the direction, so you point to the head. That's the confusing part. And to make it even more confusing, we have to also break this connection. And so we do head next equals to none. That's it. And now we will have to also store the new head. Yeah, since this is returning something, yeah, it's returning list node element, and we also have to return it here. Okay, so let's see how it goes. And here we were beating 80% in memory, and now we only beat 15%, and look, we are even slower with this more advanced approach. Yeah, but this is not really something to worry about, since I rerun it and we now are both faster and use less memory. And that only means that they have used too little test cases and they are not varied enough because we have such a huge variance in results just by 2 tries. Yeah, so sometimes they haven't prepared enough test cases and those results are not really that accurate, but generally this approach is uses more memory, and we would usually prefer the iterative approach, but still recursion is used all the time in lists, trees, graphs, and so on. That's why it's very important to train it and to understand it very deeply.